Rubin Observatory Legacy Survey of Space and Time LSST will measure billions of sources in 6 bands repeatedly for 10 years. Every object becomes trajectory in color time space. This is not just a survey, it's high-dimensional data manifold. Our question is direct. Can organized physical processes like biological or technological appear as coherent deviation from the natural LSST manifold populated by ordinary astrophysical objects? So we are not searching for isolated spectral lines, we are searching for geometry, and astrobiology relevant signals in LSST is fundamentally geometric anomaly problem. What is the multiscale coherence? Noise factorizes. If fluctuations are independent between the bands and epochs, the data behave independently. But physical processes do not behave independently. They align structure across color, time, and population context. Detection is therefore not high signal to noise in one filter. Detection is identifying correlated structure that cannot be explained by independent fluctuations. Coherence is statistical dependence across dimensions, and that is measurable with LSST. To test this, we built forward simulations probing 3 orthogonal coherence axes. The first axis, color coherence, including simulations of Kuiper belt objects, surfaces, including vegetation red edge injections as surface coherence proxies in exoplanetary spectra, and these produce aligned multiband displacement, not gray dimming. The second axis is phase stability. A stable surface structure may generate repeatable light curve patterns, and the third axis is manifold distance, how far signal lies from the natural LSST color time population manifold. Different physics leaves different geometric fingerprints. We begin with the natural astrophysical case of active or inactive Kuiper belt object. We simulate spectra with planetary spectra generator and convolve them with LSST band passes seen in left. If dimming were gray, colors wouldn't change, but coma scattering alters the spectral slope seen in the left, and the object moves coherently in color space seen in the right. In our simulations, this shift is detected at roughly 5 sigma with LSST precision, so LSST is sensitive to structured spectral coherence. Next, we examine how different KBO composition maps into observable space. We simulated regolith dominated KBO surfaces, organic rich mixtures, ice dominated KBO states, and each produces distinct reflectance spectrum in left. After LSST convolution, each spectra becomes point in color space right. These points are not random, they lie on structured low-dimensional manifold. Composition introduces ordered displacements, and the coma case moves of the baseline along coherent direction. So physics becomes geometry, and the geometry defines baseline. We then simulated 700 reflected light exoplanetary spectra at 10 to 15 parsecs, orbiting M-type stars. Stellar spectral energy distributions are included explicitly. We inject vegetation red edge as a smooth reflectance modulation while keeping atmospheric scattering fixed. Each spectrum is projected into LSST color space, and the result is interesting. Detectability on the right shows threshold behavior. Below roughly 20 to 30% surface coverage, no detection. Above that threshold, detection probability rises sharply for LSST. So this is not gradual signal-to-noise ratio accumulation, it's crossing coherence boundary, a geometric transition. As the LSST is time domain survey, we simulate 1000 LSST light curves and compare their 3 regimes: noise, stochastic variability, natural variability like partially persistent, chromatic, and coherent signals that are phase-locked, cross-band aligned, repeatable modulation. In one-dimensional projections, on the metrics in the middle, populations overlap. No single metric separates them, but when we embed color, behavior, phase stability, persistence, and amplitude stability jointly seen in the right, the populations separate cleanly. Noise clusters in coherent space, while coherent signals form distinct phase-stable cluster. So coherent signals emerge only in joint observable space, and that is the power of multiscale coherence. In conclusion, detectability of astrobiology relevant signals in LSST corresponds to crossing coherence-defined anomaly boundary in high-dimensional observable space.